Hello everyone, in this video we are going to start with the analysis and design of our cantilever retaining wall system using our ASDIP retain project manager. So as we said before, we have three different types of retaining walls, and all of these types we will be working with in this course. Of course, our first example is going to be a cantilever retaining wall. So what we have to do is we just press on it, type in your project or example name. I already prepared my first example, which is example 1, to save some time. So press on it and open. Okay, once it opens, I've said that before, ASDIP is a very simple, very systematic software. It basically walks you through the steps you need to take. You have geometry, then loads, then the materials, reinforcement, and general. So basically, geometry is the dimensions of your structural components, your stem, footing, backfill, and cover. The loads are the loads that are being applied on your structure. The material, which is the material you're using, the F prime C, rebar strength, etc. Reinforcement is the reinforcement you want to use. And general is basically the project name you want to put in, the engineer that was working on this model, notes if you have any notes. So this is basically it. Now, once you are inputting your values here, what's going to happen is that your software would be automatically calculating the checks or the stability checks or any checks that you have on this side, this right side. So you have this section is separated into several parts. You have section geometry, your stability check. We said we have overturning and sliding. Our soil bearing pressure, our shear forces. Of course, if your criteria is satisfied, you get a check here. If it is not, then you will get an X. So now, before we start, we have to go to design units, make sure our units is in SI, and then design criteria. So stability, this is basically your safety factors against overturning, against sliding. You can put it 2, you can put it 1.5, depending on what factor of safety you want to take. The conditions that you have here or that you want to use, and the codes that you will be following, which is the ACI and ASCE codes. Okay, so now let's start with our materials. Now let's start with the stem. Our concrete strength is F prime C 30 MPa. Our density is going to be 25 kilonewtons per meter cubed, and our rebar strength is going to be 420. So I already inputted most of the values, and we are going to go through all of them. Now the footing, they're going to be the same values, 30 here, 25 here, and 420 here. Now when it comes to my bearing soil, the allowable bearing pressure here is going to be 200 kilonewtons per meter squared. Usually the allowable bearing pressure, we get it from our geotechnical report. However, we are going to use it as 200 kilonewtons per meter squared. Our friction coefficient is 0.5. We can get typical values based on the type of soil that we have, no silt, silt, or coarse grained, no silt, or with silt, or silty soil. It gives you an example. We can also find it from tables and books. The internal friction angle, if we go to our image here, we can see that the internal friction angle is 30 degrees. Our gamma 1 is 18 kilonewtons, and our cohesion factor is 0. So go back here. Our internal friction is 30. Our depth to neglect passive, we are going to talk about it now. Our most density is 18. Our saturated density is, we're going to put it as 20. Now, usually if you have a water table, then this is when you take into consideration saturated density. However, if you have no water table, then usually your saturated density is equal to your moist density. So now, what is the depth to neglect passive? Now, in order to explain this, we need to understand that we have two types of pressure or soil pressures that are occurring within my retaining wall system. We have something that is called an active soil pressure and something that is called a passive soil pressure. So what's happening here is that the software is asking me for my depth to neglect passive. So first of all, let's talk about my active soil pressure. The active soil pressure usually occurs here on the backfill side. So what's happening is your backfill is applying stress that is equivalent to Ka times gamma soil times H. So let's draw it in order for us to better understand this concept. Okay, just delete this. So let's say we have a footing here, or not a footing, this is our wall. This is, so this is the stress that is applied by my backfill soil, and it's equivalent to Ka gamma S times H. This is what we call our active soil pressure. Now if you go back here, on the left side we have something that is called our passive soil pressure. You can see that we have a certain depth here, which is fill soil as well, and this soil is applying a pressure that is counteracting my active soil pressure. So basically what it is doing is that it is stabilizing my structure. So of course the magnitude of it is not equal to the active soil pressure, it is less than that. However, it is a stabilizing pressure. It helps my structure stabilize. Now what is the depth that we usually take this or what is the depth that we are going to consider here? So if we go to this image here, we can read that the depth D to the bottom of the base slab should be a minimum of 0.6 meters. So this is the minimum depth that we should take into consideration. Now if we go back, so this means that the depth here is a minimum of 0.6 meter. Now in our case, the depth to neglect passive, what are we going to take it as? We're going to take it as 0 because we do not want to neglect any of this passive pressure, as it is helping us stabilize our structure. So this will be it for our materials. Now let's go back to geometry. Our stem material is going to be concrete. Our stem height, if we go back here, our stem height is 6 minus 0.7. This is my stem height. If we go here, you can see this is your stem height. So 6 minus 0.7, which will give me 5.3. Stem thickness at top is 0.5, at bottom is 0.7. So here stem thickness at top is 50 centimeters and at bottom here it is 70 centimeters. Now taper at heel side or tapered at toe side. So this means we can see here that my stem has variable thickness. So what this is asking is this variable thickness moving towards the heel side or towards the toe side? So in this image here, we can see that our taper is at heel side because you can see that it's moving this way. And this is what we usually go for because we try to cover our tapering using our backfill soil by hiding it with our backfill soil. So we usually taper it at heel side. Now let's move to footing. Now is the wall supported on piles? Usually we do that if we have very soft soil, which is not our case. So no, it is not supported on piles. My footing thickness is 0.7. We can see it from here. It is 0.7. Go back here. My toe length is 0.7 as well, and my heel length is 2.6 or 2.6. Okay, so this is 0.7. We have to pay attention to the units, and this is 2.6 meters. Now my key depth or my key thickness, what is my key depth? We said that we have something that is called a shear key, which is this section here. Now usually we resort to this section in case we want to solve some of or if we have a sliding issue. So we create a shear key in order to have friction or to have contact between my footing and my soil. This will decrease the sliding effect that I have. So this is when we resort to a shear key. However, for now, we are not going to go for a shear key uh, unless we have to. But as a starting point, we are going to start with no shear key. Now, there are other ways in which we can reduce our sliding factors, which are increasing my heel length, increasing my toe length, increasing the amount of backfill. So these are all options based on our situation, our condition, and what we need. Now we can go to our backfill cover. The soil cover at toe is, if we go back here, it is 1.5 minus 0.7. This is the soil depth from here to here. So it's 1.5 minus 0.7, which will give us a value of 0.7. Okay, or 0.8. Okay. Now the backfill height is usually equals to the height of my stem. Now, because we are using a trial version for ASDIP, we cannot go for a height greater than 4 meters, so we are going to go for a backfill height of 4 meters. The backfill slope angle, we can see that we have an angle here. However, we are not going to follow this example just in this criteria specifically. Why? Because we are going to take into consideration that we have a live load on top of my wall, which might be a road, let's say, for example, and we want to take it into consideration. So we are not going to take our slope, we are going to take our slope as 0. So now that we have covered our materials and geometry, we can move on to my loads. So we are going to start with my backfill. My backfill moist density is 18. My backfill saturated density is 20. We talked about this before. Earth pressure theory, there are several theories that we can use. We are going to use our Coulomb. Our internal friction angle is 30 degrees, and our water table height, we are going to take it as 0. Now we took our water table height as 0 because we do not have any geotechnical report that gives us detailed information about our water table. However, if we do have such a report, then we have to consider our water table. Why? Because we talked before that we have, so here we said that we have our backfill pressure, that is Ka gamma SH. Now if we have a water table, what we are going to have here is we are going to have a water pressure in addition to my backfill pressure, or my active pressure, and my water pressure is going to be equivalent to gamma water times H. So this is why it is very important to pay attention to my water table result. So let's just draw it in a better fashion. Okay, gamma water times H. However, here we said again we do not have any information with respect to our gamma water, so we are going to put it as 0. Now we are going to move to our surcharge. Now surcharge is basically the loads that are being applied on my cantilever wall system. Now we have a uniform surcharge, which is this here. We are going to put it as 10 kPa. Our strip pressure, which is this pressure here. Now we are not going to have any strip pressure. We are going to take it as 0. However, usually when we take loads into consideration, we need to pay attention to the load that we are working with. So for example, we might be working with, so our wall might be placed on a footing, and the load that is distributed throughout this footing is distributed throughout its length. So what's happening here is, so let's say I have this footing here. This is my wall, my footing. So my load is going to be distributed along the length of my wall, which is basically a linear load. So we have to pay attention to the type of load that we have. In this case, it's a linear load. Or if we are working with a road, then my road is going to distribute this load as an area load, and we might even have a point load. So we need to know what type of load we are working with when we are determining our pressure. Now, we said we are going to keep it as 0, so no strip pressure here. Now concentrated, again, we do not have any concentrated load. Usually the case of our concentrated load is if we have a column coming out of my wall. This is usually the case of basements. If you're working with basements floor, this is what happens. Now, wind and seismic load. So we have the option to check for wind and seismic load, to check for lateral loads. However, here we do not have any lateral. We are not going to take lateral loads into consideration. But in case that we wanted to do that, we have the option. ASDIP provides us with the option to check for lateral loads as well. So now that we are done with geometry, we are done with loads, and we are done with material, we have one last thing to go through, which is reinforcement, and we will keep this for our next lecture because we want to talk about our reinforcement in details. So this will be it for this lecture. We started with the analysis and design of a retaining wall system, cantilever retaining wall system to be specific, and in our next lecture we are going to continue with our reinforcement, and we are going to check for our criterias if we were able to satisfy them or not. So I'll see you in our next video.